Okay, so here's what we were talking about last time. We were talking about integrals. Talked about the importance of understanding integrals as Riemann sums. The very short summary of why that is. It's because, and certainly coming from the point of view of engineers and economists and other applied parties that make up the vast majority of this class, it's because applications that you can compute with integrals most directly connect to Riemann sums, not to area under a curve. If you're computing the amount of work that it takes to perform some task, there's no area in that question, right? So you need to have something applications connect to. And you can take these kinds of questions and you can break them down into little pieces algebraically, and that process creates this sort of a construction, a Riemann sum. That's why it's important that integrals be defined as Riemann sums. At least that's why it's important from an application standpoint. Okay. All right. And we made the observation that, roughly speaking, this is what happens in a Riemann sum. And we simply asked, what if you have a different kind of a domain? What if your domain, instead of being an interval, a one-dimensional interval on, let's say, the x-axis, what if it's a two-dimensional region, let's say, in the xy plane? What would such a chopping up look like? And we made this this observation here that you take this domain, two-dimensional domain in the xy plane, and you can chop it up into little pieces. Now, the chopping process is a little different. In some sense, you have to kind of chop it in two different directions. Right? But still, you can chop it up into little pieces. You can still talk about the size of one of these little pieces. Size, of course, in this context, the size of one of those things is area. That's how we talk about size in a two-dimensional context. Right? And with that in mind, here you go. There's what that area is. Here's the function that you're multiplying it by for whatever reason, depending on the application. We'll see some applications in a couple moments. Here's adding up over all the pieces. Now I emphasize adding up over all of these pieces. So don't just say summation I goes from 1 to n. I goes from 1 to n only takes you sort of in one direction. But you also have to go in the other direction. And furthermore, for each value of I, you've got to go in the other direction and have this other index j that goes from 1 to n. And then for the next value of I, you've got to let j go from 1 to n, etc. Right? So you literally have two indices here. Sometimes this gets called a two-index Riemann sum. Yeah.
What's the limit from?
Oh, yeah. So this will be the limit as n goes to infinity. And each of these I and j goes from 1 to n. Yeah. Right. Okay. So there's your Riemann sum. We talked about integral notation. Again, this notation is just a shorthand for the Riemann sum. That's just as true back here. This notation here is just shorthand for pretty much that notation. I mean, after all, what is an integral? It's a Riemann sum. So having a different notation for it, I mean, it's still the same thing. It's still that Riemann sum. So the notation is just shorthanding the item that we're actually talking about. Okay, so I think the notation's pretty plausible. Okay. All right. So now I want to emphasize, here's what we've done so far. I mean, our goal is to take applications and be able to get number answers. All we've done so far is we've talked about breaking up applications into little algebraic expressions called Riemann sums that we then define to be double integrals. But it remains, what we have not yet done is address the question of how would I numerically compute one of these double integrals. We haven't talked about that yet. We'll get there. Right? I don't want to get to it too fast because I want to focus on the very important and very non-trivial idea of how do you connect applications to Riemann sums and what are these Riemann sums, etc. Okay. All right. So don't worry about the numerical answers just yet. Okay. Right. So let's see some of those applications. Here are I'm going to give you 3 of them. The first one is going to be a little bit familiar. This is kind of a one dimension up analog of the very familiar idea of area under a curve. Right? And so I know you all know with a single variable integral, the big application / interpretation that you have for what is an integral is it's area under a curve. I know that's how people tend to think about it. Unfortunate though I think that is. Right? But anyway, so this is sort of one dimension up. This is volume under a surface. Right? So specifically a graph. So if you have a surface that is a graph, and notice what I've written down here, this is literally, we've taken some function of 2 variables, x and y, and we're setting its value equal to a new variable. That's literally the graph construction. Right? Don't try to use this to compute volume under a level set. It's not a thing. Right? That's not what integrals, it's just a very, very different situation. Right? Okay. So if you're looking for volume under a graph, well, we're going to take the domain. Here's our domain down here. I could talk about chopping up that domain into little pieces. Right? And having chopped up the domain into little pieces, notice that for each little piece of the domain, I'm implicitly then restricting my attention on the volume to, well, the volume sitting over that little piece of the domain. We can ask, well, how much volume is there sitting above that little piece of the domain? And how much volume there is something I can write down without too terribly much trouble. It's a pretty easy pitch that the volume is equal to height, which is z, which is, of course, the value of the function because we're looking at a graph, because z equals f is how you make graphs. There's the height, and then times the area of that base, again, old high school geometry formula, the area of this base down here, dA. Right, easy pitch. Right, and then, of course, what I want to do is I want to add up all these little pieces of volume, and here you go then. So we have an integral that represents that total volume. Now, don't forget, integrals are Riemann sums. So let me rewrite this now just to emphasize what is the Riemann sum that we're dealing with when we write this down. Well, the Riemann sum is limit, summation, indices, etc. And we'll have f xi star yj star delta x, delta y. There's our Riemann sum from the previous page, right? And so again, the height, you can see right there, value of the function. The area of the base, there it is, right there. I should have used a different color. Oh well. It's a Riemann sum. It's literally the same Riemann sum, right? So if I write it as a Riemann sum, okay, there it is as a Riemann sum, but this integral shorthand represents the same thing, and it's convenient, a little bit more compact representation, but it's the same thing. Okay, so it's perfectly fine to just use integral shorthand notation. No problem. Everybody does it. It's what the Riemann sum is in the first place. It's fine. It's not a problem at all, right? Just don't make the mistake of forgetting what this means. Like when you write down a double integral, what you were writing down is this Riemann sum right here. Right? It's this expression. You're taking literally little pieces of area, multiplying them by heights, adding up over all the pieces, and taking a limit as it goes to infinity. Okay. All right. Yeah.
What would the bounds for the integral be if you weren't?
Oh, yeah, that's a whole other question. Yeah, we'll get to that. Yeah, exactly. For the moment, we don't have bounds exactly. For the moment, our definition of a double integral is whatever the domain is, whatever that domain is, let's call it D, just make that a subscript. And that subscript is an indication that that's what you should use to compute whatever necessary details you need in this Riemann sum. And so again, how you get to the actual, but I want to compute this, and dear God, I hope I don't have to actually use an actual limit of actual summations. Oh my God, that'd be a nightmare. Yes, and there is a way around it, and yes, we're going to talk about how bounds will kind of factor into that, but at the moment, we're not doing that just yet. Okay. Right, okay, so here's another example. By the way, going forward, I'm just going to use integral notation. I'm not going to use Riemann sum notation. It's just easier. Okay, so suppose I have a two-dimensional sheet that has mass in it somehow. So here's a two-dimensional sheet full of a bunch of mass, and I'm going to represent the different mass density by there being maybe a deeper color over here. Maybe even we'll get into the orange and then some really dark orange down there, right? So there's kind of a heat map, if you will, representation of density as a function of location on that rectangle. And how would I compute the total mass? Well, I can't multiply density times area because density is not constant. Right? But what I can do is chop up this rectangle into little pieces. I can argue on each little piece. I could compute the amount of mass. I could talk about adding up all the little pieces of mass, therefore, to get the total mass. And I could also talk about how on each little piece, the amount of mass in that piece is the density at some point in that little piece of area. Density times size, namely area. Right? So if you know mass per unit area, I mean, mass per unit area times area is mass. Right? Okay. So we likewise can write that down as an integral. Here it is, that integral. And notice mass per unit area times area gives me little pieces of mass. And when you add up a bunch of little pieces of mass, you get the total mass. So still a Riemann sum. Different application. While I'm here, let me observe. Notice in this discussion that we just had here about computing mass on a sheet, notice no discussion of volume anywhere in there, right? So it's completely unnecessary and, in fact, counterproductive if you were to take the point of view of, look, double integrals are fundamentally volumes. I want to think about everything in terms of volume. And then if you were to try to make some really contorted discussion about how, well, if you thought of density as a height, kind of. And then if you were to, can't you see if you blah, 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 and try to relate volume, which is not intrinsic to this problem, to the mass that you're interested in. And maybe you could kind of sort of do it in a way, but it'd be sloppy. And you'd still be using Riemann sums, and therefore it's totally unnecessary. Okay. All right. Okay, so we go straight from the application to the Riemann sum. Okay, how are we doing? Everybody's good. Okay. How to compute this? Separate matter. We'll get to it soon. For the moment, let's not worry about it. Population. Suppose you want to compute the population of, Colorado, or maybe Wyoming. Take your pick. Right? Or any of countless counties out in West Texas. Right? You want to compute population. Well, one way we understand population and how it's spread around on an area is to talk about population density. Right? So this, what we call population density, population per unit area. People live on area, right? Pretty much. And so per unit area is a way to naturally make sense. I mean, it would be kind of weird to talk about population per unit volume, right? How high up do people live? Usually whatever. Usually we don't care. We talk about where people are by their longitude and latitude. That's we talk about people living on area, right? Population per unit area. And population per unit area times area gives you little bits of population. And so if we were to take this state or county or whatever it is and choppity, right? And then if we were to add up the population, how many people are in each one of those pieces? Add up over all the pieces. That gives you the grand total number of people. Right? Real easy way to keep track of things. And so integral. Everybody on board? So there's bazillions of applications, bazillions, right? These are just 3 quickies, right? But it's not hard to use your imagination and see how, if you want to compute a total amount of a certain kind of stuff, whether that stuff be population or mass or volume, whatever it is that you can associate to locations on an area, right? If you want to compute stuff spread across an area, it's going to be stuff per unit area times area to get stuff, and then you add up over all the pieces to get the total stuff. I mean, it's the same strategy, same argument each time. It's a very sort of a quick and dirty way to understand Riemann sums, but that's really kind of what's going on. Okay, so lots of applications. There's lots of kinds of stuff out there in the world that we care about, and that it tends to spread out over area. Right? A very, very, very natural type of arrangement of stuff. Okay. All right. So lots of applications. By the way, again, while I'm here, before I go on, I want to broaden your minds a little bit on the notion of the word density. Right. So if y'all took 8th grade physical science like I did, they drilled into my head at a young age that density was mass per unit volume. Mass per unit volume, and that's what density is. And I had to memorize, what's the density of, various different kinds of rocks or metals or something. I forgot all of it. Yeah. But fundamentally, that was the point of view that I was given on density. That's not how the word is used in general. Right? So heads up about that. Density as a word is used to mean any kind of a quantity of some sort. Per unit size in whatever sense of whatever sort. Right? So here, maybe we're talking about mass, sure, but we're not thinking of the mass as spread out over volume. We're thinking of mass as spread out over area. So we talk about mass per unit area. That's a kind of a density. Right? If you go to the hardware store and buy chain, right, they will talk about the mass per unit length of the chain, because that's how you keep track of how much chain you have, right? If you have chain of a certain kind, they measure off 3 feet of that chain. That's how much chain you got there. I have 3 feet of this chain, right? You measure chain in terms of length, but it still has a mass. So if you have a chain and you're interested in its mass per unit, how much chain you have, you're talking about mass per unit length. Right? And the mass per unit volume of the metal itself that makes up the chain, who cares? That's not how I keep track. I don't keep track of how much chain I have by how much volume it takes up. Nobody does that, right? That's not how you use chain. So depending on the situation, depending on the problem, size could be either volume or area or length. And you gotta, adapt to the situation. The stuff could be mass per unit area or volume or length, or it could be number of people, number of bacteria, what have you, per unit length, per unit area, per unit volume, right? There's lots of different kinds of things. So anyway, heads up, we're going to be using that term density very broadly, and always interpret appropriate to the context. And I mean stuff per unit size, stuff appropriate to the application, size appropriate to the application. Okay, so I'm going to do a little tangential calculation here. We computed volume as a double integral, and that's nice. We didn't actually compute it, but we wrote it as a Riemann sum. I want to do another calculation of how, given a graph, right? How would I go about computing the volume under that graph? So here's one way you could do it. We could take a dy integral. This is Calc 1. Or Calc 2, I don't know, depending on where you break it up. Let's call it Calc 2. So this is a Calc 2 integral, and y'all will probably recall that if you were to take the cross-sectional area, right, cross-sectional area, and multiply by thickness of little slices, like think of this as a great big loaf of bread, and you slice it up into a bunch of little slices of bread, and then the volume in each slice of bread is area times thickness, and then add that up over all of slices of bread, that gives you the volume of the loaf of bread. Right? Y'all remember those kinds of problems? And in Calc 1, Calc 2 classes, those areas are nice, simple areas. Maybe they're squares. Maybe they're equilateral triangles, whatever. Very often they're circles. Very often we're taking, like a rotated solid, right? And then those slices are discs. And then, pi r squared and all that business. Right? So a bunch of different versions of that. So in this situation, we're going to try to apply the same idea. Volume is a dy integral of cross-sectional area. By the way, notice that area is a function of y. Right? For any given y, at that value of y, you can talk about its cross-sectional area at that value of y. Okay, and now we're dead in the water because we don't recognize this cross-sectional shape. It's not a square, it's not a triangle, it's not a disc or an annulus or any of those familiar, what I like to call barnyard variety geometric figures that we can just write down a formula for and proceed. So what do? Right? We're kind of toast. A lot of food metaphors for me this morning. That's probably means something. I guess I'm hungry. So how do I compute that area? Well, here's the thing. That area, here it is again. That area is the area under a certain curve. And that curve, there it is again. That curve is just a cross-section of that original surface. So I'm looking at the area under a curve. Area under a curve. Want to compute the area under a curve. Where have I heard that phrase before? Area under a curve. Oh, yeah. Area under a curve is an integral. That's how you compute the area under a curve, right? So here we go. If you want to compute the area under a curve, you go in that direction. Now, so notice we're going in the x direction. Here, let me make a better artistic choice here. I want to use highlighter. There we go. We go in the x direction, and we do an x integral as we're going in the x direction. And we compute area as, well, an integral of height. Right? Well, that height, we just got through agreeing. We're talking about height up to that curve. That curve, of course, is part of this surface. And that surface is z, aka height, is f of x comma y. So it's the value of the function f. That's our height. So we compute that cross-sectional area with an integral. Yeah? Everybody good? Okay. All right, now do notice while we're doing that, while we're computing that cross-sectional area, let's see here we go. Don't forget y is fixed. Right? Y is, it is for a specific value of y that I'm computing that area. So this y that we're plugging in there, that's not changing for the purposes of this integral. It is specifically for a single one fixed value of that y that I want to know the cross-sectional area for that y. Right? So so this, when you look at this integral algebraically, it seems a little kind of wrong. Like, can you have two variables in an integral? Point of order, we don't have two variables in this integral. Y is a constant for the purposes of that integral. Everybody cool with that? Okay. So there we go. Then we have an integral of an integral, if you think about it, right? So we were computing the whole purpose of this A integral is to compute that cross-sectional area, which is inside of another integral. And so altogether, I have a dy integral, right? As I move in the y direction, I have a dy integral of, well, what is a dx integral? that dx integral because it is that cross-sectional area. Integral of an integral. Seems a little weird, right? Nevertheless, that's something you can do, and you can totally compute this. I mean, this is just a matter of punching it up. So you've got a f of x and y, and we're going to treat y like a constant. So this is just a function of x. So you can take an x integral, knock yourself out, just ignore the whole y integral on the outside while you're doing that x integral, and what comes out is a great big function of y. Right? In fact, you see it right there. It's a function of y, and with a function of y in there. This is blue, but with that function of y, we take the integral with respect to y. That's not a problem. Y integral of a function of y, punch that up, right? And out comes an answer, and we just computed volume. Okay. Okay, we'll just see an example in a minute. So great, we have an actual, feasible way to compute volume, and that's kind of nice. Good news, I suppose. Let me criticize this result. I've already sort of made the joke that, but how often do we actually need that? Volume is not our goal here. It's not our goal to figure out, oh my gosh, there's all these volumes I need to compute. How am I going to do it? No, our goal is to compute all the other stuff. We want to be able to compute works and populations and masses and all sorts of other stuff that accumulates over areas. Volume is just one, arguably not that interesting example. So I've computed something that I arguably don't really care that much about. Okay, so is that the point? No. Here's the point. I've also already argued that volume can be computed with a double integral, if only I knew how to compute them. Right? Well, here's the thing. If this is equal to that and that's equal to the other, then this is equal to the other. Yeah. So these two things are equal, and this is deliberately non-rigorous discussion, and I feel a little creepy doing it, but this is perfectly appropriate for Math 212, and there are some points of rigor that I'm completely ignoring and sweeping under the rug, and again, I think Math 212 appropriate. Okay, so this is really the big punchline, though, for us, is that not only do I have a way to compute volume, I guess that's nice, but now I have a way to compute double integrals. And all of these applications here, not just volume, but if you want to compute the mass of something, okay, cool. Well, I can rewrite mass as a double integral. And now I have a way to compute double integrals. Oh, I want to compute the population of Wyoming. Okay, well, I wrote it as a double integral, and then I kind of don't know where to go from there. Well, now I have a way to compute that double integral, too. Okay. So that's the big point here. By the way, this construction we just made is called an iterated integral. In this book, at least, I think that's the more common term. It's always bugged me. To me, an iteration is where you redo the exact same thing. And I think it's important to notice that that's not what we're doing here. We're doing an x integral, and then subsequently, we're not doing another x integral. We're doing a different kind of an integral. So to me, the term iterated integral is a little bit, it's just a little bit of a mismatch. I like to call these nested integrals because it's literally like the whole Russian nesting dolls thing, right? This is something inside of another something. The nesting does not suggest that they are identical. So I tried to popularize the term nested integrals. I don't think it's going to take off. It's been 20 years now and it has not gone viral. Oh well. Anyway, in this course, the term is iterated integral, and I accept that. Okay. All right, so let's do an example. Here we go. Suppose I want to compute the amount of mass in a sheet of some metal alloy, whatever, and it has a non-constant density given by this formula. Right? So depending on where you are on the sheet, depending on your x and your y location, totally different formula for density depending on where you are. Okay. Well, old news. Mass is computed with double integrals. We knew that a long time ago. Well, several minutes ago. Next, and this is the very, very recent news just from the previous page. Double integrals apparently can be computed with iterated integrals. Cool. And iterated integrals, I can straight up compute. By the way, I glossed over a detail here. The range of values of x. It's the range of values of x on the interval that we're typing. I mean, if you look back at the picture, right, I mean, you're slicing up over the rectangle. The rectangle has x going from 1 to 3. So no surprise, that's the x bounds on the integral. Likewise, the range of values of y. Well, for each value of x, you're going to look at those corresponding values of y. Okay. And then we proceed. This inside integral, I can compute, ignoring all the x business on the outside. I've got a function of y here. Do be careful about one point. Y is our variable. When you are taking the antiderivative of x squared, you're going to have this reflexive urge to write the integral of x squared as 1/3 x cubed. But don't forget, for the purposes of this inside integral, this dy integral, we have to treat x as a constant because it is a constant for the purposes of its inside integral. That's why we're computing that inside integral. It's at that value of x. For that value of x, we want to know cross-sectional area as a function of x. And so x is a constant. And so the integral of a constant is constant times variable. So in this case, x squared times y. Yeah.
So, I just saw in like the blurb you said it doesn't matter the order.
Yeah. That's right. Forgive me. I should have. I kind of slipped over that. So you can do the slicing in either order. Here, I happen to arbitrarily, for no good reason, it does not matter. I did my y slicing. I'm going to say I'm going to say first momentarily on the outside. I'll say. And then for a given value of y, I then had to ask the question of what the cross-sectional area is. That's my x slicing. Yeah, so I happen to choose that order. But it doesn't matter.
Okay.
You can do it in either order. It's a good catch. Thank you for noticing that. So let me suggest this. Draw the pictures correspondingly. Do this development of ideas correspondingly for this exact same question that I have written here, just doing the slicing in the opposite order. Make sure you can see what those pictures are and do that development. Yeah. Okay. Be a great exercise for everybody. Okay. Yeah. So here it is. So we do that integral. The antiderivative of x squared is x squared y. The antiderivative of y squared, well, y is the variable, so that's exactly what you kind of wanted it to be. It's 1/3 y cubed. Easy peasy. Okay, but do be careful about this one. I mean, that kind of thing. Lots of students will write 1/3 x cubed, and it's completely wrong. Makes no sense. It's got nothing to do with what we're actually doing in this question. Right, so be real careful about that. Always got to watch out for which variable is where. Okay. So now plugging in, so here are the numbers to plug in, 2 and 4, and here's another common mistake that students make, is they start plugging in these numbers 2 and 4, and okay, well yeah, but you got to remember, we're plugging in for y, right? So this 2 is actually y equals 2. This 4 is actually y equals 4, right? So plug in these values 2 and 4 for y specifically, right? So that goes into there, and it goes into there. It does not go into there. A lot of people just start plugging it in for every variable they see. That 4, let's just keep putting those 4s in there, right? Everywhere they possibly can. That also doesn't make sense, right? So my hack for that is I don't just recopy 2 and 4 over here. In order to help my memory, in order to avoid the inadvertent, absent-minded wrong plug-in, rewrite these as y equals 2, y equals 4. Emphasize in your writing what it is that you're plugging in for. So this is not required, but this is strongly advised. This will help you protect yourself from yourself. And we all need help with that. So, yeah. Okay. So you plug in, and now notice that we didn't plug in anything for the x's, and so there's x's in our answer, and now we have, it seems weird to do an integral and have the answer be a function. Seems kind of wrong, but notice, no, it's supposed to be. This inside integral, the whole purpose of that integral is that it would be a corresponding function, that it would be the function that is the integrand for the outside integral. And so it is, right? Look at that. It is the integrand for this outside integral. And then proceed along, do your second integral. This is literally single variable calculus at that point. There's nothing even constant to be ignored. It's just straight up Calc 2. And so there you go, and you get an answer. Okay, how we doing? Everybody happy? Okay. A little bit of terminology, real quick, super quick, on this. There's a temptation to call these two integrals the first integral and the second integral. There's something a little bit awkward about that. It's tempting to call that the first integral because that's the first integral that you write down as you're developing it. It's the first integral in your slicing process. And then after you write that down, then you secondly write this down as the second integral in your, what you might call your slicing process. Right? But then notice what happens when you're computing. When you're computing, that's the first integral that you actually compute with. In the calculation, it's first. And only after having done that do we have the integrand for, and can we therefore actually compute the integral of the second, you might say, integral. So this terminology, first and second, is extremely ambiguous. It's not clear. What do you mean? Which one? First? First in what sense? First in the computation? First in the slicing? I don't know what you're talking about. Right? So in order to get around that little awkwardness, I like to call them the outside integral and the inside integral. That's clear. It's unambiguous. Okay. Okay. So, a lot of students at this point think to themselves, oh, well, look, I was computing mass, and the ultimate punchline of how I computed mass was with this iterated integral. What purpose anymore does the double integral even serve? Why should I even bother writing down a double integral? I didn't compute anything with it. Isn't that just wasted pencil lead? What? Can't we just call that a regretful first, naive venture into this problem to be, replaced by this idea of an iterated integral that's clearly superior? And no, you can't. It doesn't work. And let me try to explain why. It is because in this calculation here, the geometry of this calculation is peculiar. It is unique to the question of volume, that we can write down that there's this intermediate notion, if you will, of area. Right, that there isn't sort of an analog of that in, let's say, a mass problem, like we're going to see on the next page in just a moment. So it makes perfect sense for me to say that, look, if I'm chopping up volume into little pieces, the first kind of chopping I do slices it up into little bits of area, and I know things about area, and I can further develop the idea from there. Okay, because what you might call volume per unit area, namely height, is a concept that I can draw a picture of, and furthermore, volume per unit area, namely height, times length. Oh, come on, elbow. Is, again, something I can talk about and make sense out of. Right? Volume per unit area times length is area. Familiar notion. That's intrinsic to the geometry. Now, by comparison, let's go over here and look at this situation here. This is mass per unit area. If I were to jump down here and say mass per unit area times length and ask, what is this? What is mass per unit area times length? That's not a thing, right? I mean, you might argue that from a unit standpoint, mass per unit area times length is mass per unit length. But what does that look like in the picture? How do I relate to that? What is it? Is How much does mass per unit length weigh, right? What is this thing physically? How do you know that whatever this thing is, that it's something that could be an integrand for another integral, and what would the result of that integral be? I'm just saying it's not clear what that is, right? And that's because this application of mass doesn't have this intermediate notion like area does. Excuse me, like in the volume calculation, we have this intermediate notion of area. It's the lucky break of the geometry of this situation, right? And we just don't get such a lucky break here. So if you try to argue directly to this, I don't know what you're talking about, and I don't think you do either. That's the little sticky wicket there. Okay, so we desperately need this notion of double integral. This makes loads of sense. I'm taking mass per unit area and multiplying by area. That's why we talk about mass per unit area, is so that I can multiply it by area to get mass. There's nothing weird about that. That's all natural, it's all meaningful. And I can then argue just from an algebraic standpoint that, well, double integrals can be computed with iterated integrals. Thank you, algebra. And then I get to the iterated integral that I want without any highly dubious arguments about physical concepts that don't exist. Okay. All right, so make sure to give me the double integral. I want to see that double integral. If you're doing an application, I want to see the double integral as part of what I consider to be a meaningful argument about how you're attacking the application in question. Okay. Okie dokie. So here's going to be our sort of breakdown then. This is our sort of strategy of how to solve application problems. Step 1, you rewrite your application as a Riemann sum, aka double integral. That's first. Okay. Next, you argue that your Riemann sum, aka double integral, can be rewritten as an iterated integral. That's number 2. And then number 3, that iterated integral you can compute with, good old fundamental theorem of calculus to get a numerical answer that you can actually, do business with. So 3-step process. Everybody on board? Okay. We've spent a bunch of time already. Well, we spent some time talking about part 1, phase 1, as I like to call it, phase 1 of a double integral argument, writing applications as Riemann sums. That's usually going to be pretty straightforward. Phase 2 is going to be, as it turns out, a harder question for reasons that will become clear in a couple of minutes, time permitting. Yeah, we got good time. So phase 2 we're going to have to actually focus on. It's not always as easy as it was in this example. And then phase 3 is usually just plug and chug. Keep track of what's a constant and what's a variable, and then remember all that Calc 2, anti-differentiation trickery that you use, integration by parts and substitutions, trig substitutions, and all. Oh, and hey, if you are shaky on trig substitutions, I have a recording in my YouTube channel in the miscellaneous topic sections about trig substitutions. I think everybody should know trig substitutions because trig substitution susceptible integrands come up whenever there are circles in the problem and the world is full of circles. And that's my motivation for that. So as a former physics major, I encountered just tons and tons of trig substitutions. I'm a big believer. Make sure you know how to do trig substitutions for this class. Yeah.
Those are as in sine squared plus cosine squared equals 1, or
where you're using those tricks to help you do certain kinds of antiderivatives. Yeah, so certain antiderivatives where square roots of awkward expressions are involved. It turns out there's clever ways you can use trig substitutions. Yeah, right. Okay. So next question: what if your domain's not a rectangle? Right. So maybe you want to compute the mass of a thing. And that thing, it just doesn't happen to be shaped like a rectangle. What if you want to compute the population of a state other than Wyoming or Colorado? Right? Suppose you want to compute the volume under the graph of some function, but as sitting over some other shape. that isn't a rectangle, right? It's a very reasonable question. And the short answer is it's going to be a double integral. We're still going to chop it up into little pieces. Right? And it's just that when we talk about adding those up, we're adding up over, kind of a different, like this little piece right there. We're not interested in that piece because there's no metal on that piece. That piece is not part of our state of whatever state that is. Is that Kentucky? I don't know what that is. Right? It's something. Non-rectangular domain. We can't use quite the same definition. This is not a Math 212 appropriate thing to worry about. So don't worry about the definition. A double integral over a non-rectangular domain, it's exactly what you think it is. Chop up that domain into a bunch of little pieces. Do the computations on each little piece. How much metal is there in that little piece? Density times area, it's exactly the same, right? And then add up over the actual pieces that you actually have. So that's the way I want you to think about a double integral for a non-rectangular domain. You're just adding up over those actual pieces. How you compute that, good news, it's just like with a rectangular domain. Just for visualizing purposes, let's imagine you have a volume sitting up over there, right? Sitting up over this area, and you chop that volume up into little pieces of volume. You're going to have cross-sectional areas. Something like that, right? This is the cross-sectional area that you're going to multiply by the thickness as you go in the x direction. You'll talk about little pieces of thickness, delta x, etc. Again, likewise, we're going to compute this cross-sectional area as y ranges over certain values, and as y goes over certain values, we're looking at the heights, etc. There's your dy. So it's just the same. It's the same kind of thing. There's only one little microscopic, micro difference. This is hardly even a big deal. But now let me erase the picture here. The one little difference is that for a given value of x, right, somewhere between a and b, for that given value of x, the range of values of y, these y bounds for your y integral, change. Right? So there's your lower bound for y. There's your upper bound for y for this value of x. Right? But what do you think is going to happen when this x moves over a little bit? If x moves over to here, different value of x, well, then elbow. Then you're going to go from there to there, and you're going to have a different y1 and a different y2. So the punchline is really not that big of a deal. These y bounds depend on what x are you looking at. Different x's, you get different y's. Said differently, the y bounds are functions of x. That's the only difference. Everything else is the same. Inside integral, outside integral, cross-sectional area, the whole shebang. Okay. Or vice versa, if you're slicing the other way, if you're doing your y integral first, right? Y goes from c to d. Then for a given value of y, some value of y, your x bounds are going to depend on what y you're at. And I appeal to your geometric intuition. As y changes, like as y increases, as you're going up in that slice, well, those x bounds move around depending on the shape of your domain. And so their x bounds are functions of y. In general, whatever is your inside variable, the differential for your inside integral, I'll call that the inside variable. The inside variable is going to have bounds that are functions of the outside variable. And that's the whole twist. I mean, it's really morally the same. Alrighty, and I'm out of time. Ran out of time. Okay, so we'll pick up here on Monday. Y'all have a great weekend. Final reminder: don't forget to turn in your homework tonight through GradeScope. Apparently, it's been done successfully, so you should have no trouble. But make sure to get it done. 11 p.m. is the cutoff time. You got to get it in before 11 p.m. You can't turn it in late. Okay, see y'all later.